started. So any questions about last time? Okay, I have a couple of remarks before we move on to the algebra of these spaces. Is a couple of remarks about the distance formula. So that is the distance formula for an dimensional space. Unlike to everything up to dimension 3, this is not a formula per se. It is, in fact, a definition. So keep that in mind. So unless we are referring to directly or indirectly to the space we're living, either no matter what dimension it is, you still a line is still a line. Okay, so you can still say that you are measuring. You have a geometry that reflects on a line that reflects the real life what's happening on the road. If it's on the two-dimensional, it's something's happening on the plane, and three-dimensionally is our space. Okay, so in that case, the function, the formula, it is a formula. Okay, a formula that it gives you the distance to be computed rather than to be measured if everything else has been pre-measured. Okay, so it's a convenient formula, which is pretty much the one at the top. How you, once everything is pre-computed, pre-measured rather, you can evaluate the distance. Okay. However, beyond that, since we cannot make a reference to anything specific in life, then what we're doing here, we're saying that this is a definition. Suppose we have made up an abstract space of dimension 4 or 5 or higher, and then we say, well, this is how we want to measure distances within this space. So it is entirely our choice, and there are other ways to do it. So we'll let you mention one, and that is measuring distances through simply absolute values, difference of absolute values with no squares. Okay. So this is called the Euclidean metric, and this is called the taxicab metric. Okay, so another way to measure it. So if you are in a city which is cut into these into blocks, you cannot go diagonally. So Euclidean, it's not like in the field, which is what Euclidean metric is about. You measure the distance. The shortest distance is a diagonal. However, in a city, you have to follow the streets, and that's how you measure it, right? So it will give you like this. The distance is the sum of this. This is P and Q, and this is how you compute the distance. You do not go straight, but you go one and the other. Okay, so the point being that, once again, we could have, depending on what kind of problem we were solving, we're solving mathematically a problem that may have come from elsewhere, and that we might pick one or we might pick the other. And it is entirely up to us, and the nature of the problem dictates the mathematics. Okay, which one, we don't know. Unfortunately, it is the formula is so nice, so the alternatives might be overlooked. And let me give you one example. If we go back to prices, so the space of prices is made up abstract space. So once again, we should not probably refer to our space as some kind of analog of that. And then for example, you have two situations. These are the prices, collection of prices, maybe just two, and then the other one. Okay, how do you measure the distance between those two situations? It's tempting just to take the formula over there, and that's your distance. So you can say, well, these are situations similar to that situation because that number d is so small. Okay. However, unlike the physical space, remember the units are not the same necessarily. Okay. So switching from feet to meters in the Euclidean space will rescale all of the x's, and therefore proportionally things won't change. So your distance measuring will be still valid. Your distance will be simply now, instead of feet, it will be in meters. That's all. However, if you were talking about prices and then these are dollars, then switching from, remember it was wheat per bushel and sugar per ton. Okay, so if I switch from ton to pounds, for example, everything changes. I just switched to price of sugar and different measuring, and then the distance, that distance on top or the second one will change entirely. Okay, so that it means that your seemingly trivial step of changing how you measure the price changes your distance in that abstract space. Okay, so you certainly don't want that to happen. It is imagine similarly you take stock prices. So they might have similar prices may not have changed. Two different stocks. The prices might be changing similarly, but the actual where they come from, it all depends on the actual price. The whole number of stock has been issued. Okay, so then once again, if you have to rescale somehow these two or more stocks in order to actually make this measurement fair. Furthermore, it could, that's in economics. You can think about examples in computer science when you collect information, you're comparing either you make an image comparison, or you do string comparison, say maybe two texts comparing them, and then you can measure all kinds of attributes. And once again, you have n attributes, and then once again you can compare them one by one, and using Euclidean formula. And once again, because of this similar situation, for example, you can measure, how they try to prove, for example, that those unattributed texts were indeed written by Shakespeare. Have you heard of this? You do comparison, and the frequency of words is compared. Okay, so that could be, you take 1,000 words, so n is equal to 1,000, and what is the frequency of one word against the other? Okay, and then if you compare, if it is similar, then it might be probably more likely to be Shakespeare than not. Okay, and there is some candidate maybe who is also claimed to be in fact the author, and then there's a mismatch. So Shakespeare is closer to this text than the other guy. Okay, so that makes sense that to say that, well, we probably can conclude depending on that distance the likelihood that the author was Shakespeare. Okay, so that's what you also done all the time, or Google search, whatever. So same problem up here. You cannot use this formula without thinking ahead, because scaling, because of the different proportions. Even worse, or so, you could end up with different units. So imagine that attributes are measured in different units. So what's going to happen with the formula? Well, I'm comparing two persons. One who is close to the other. One in two attributes. One height, the other one is weight. Okay, so these are the two numbers. Okay, so I'm applying the formula, pretty much the formula that from R2, this formula. Okay, so I subtract the weights to compare the two persons. Subtract the weights squared, subtract the heights squared, add, and then takes the square of what's going to happen.
It won't really tell us anything, right? Because you could have two people with different heights, different weights, but that metric gives us the same number.
Well, it might be. It is certainly valid critique. There's a bigger problem. Anyone? So once again, the first x is measured in pounds. Y is measured in inches. Okay? Look at the formula. The one at the top, this one.
You're adding them together.
Yes, and
you can't do that if they're two.
You cannot do that. You simply cannot add pounds to inches. That isn't simple. Well, it is insane if you don't want to go strong here, but you just should not be doing it. It probably does not make any sense whatsoever to do that. Okay? And if you want to compare people, then there are probably better way to do it. But just as an example of what can happen if you treat these nice formulas mathematically valid, we're going to do more with them. But if you are not doing your signs, before you bring mathematics into this, then you can easily fail if you just ignore things like that, like units. In fact, one other example would be space-time. Space-time, you add the fourth dimension, time, and if once again you jump in and try to use this formula, four-dimensional formula, you are screwing it up because three, these are measured in, say, inches or feet, and this one is measured in seconds. Okay, then once again you try to add them together, and that cannot work, and that's why it's done actually in a different way. So the only way, I suppose, the only way out of it is add some kind of a weights rather than simply add these numbers. You have to add some correcting weights, and then at least you correct the problem with the units and maybe others. But that's once again, it does not come from mathematics. It comes from that whatever you're trying to solve outside of mathematics. Okay, so like I said, you could the distance another possibility of the formula you can like I said, you can put a number there, different numbers for different n's, for different case rather, and so putting different weights to different dimensions. Okay, that's another possibility. So there's a bunch of them. So once again, this is 1, this is 2, and there are many ways to measure distances in Euclidean from a Cartesian system, which is just a bunch of numbers. Okay, so you can measure distances, however, in a number of ways, and which one is not predetermined. Okay, so another remark I want to make about this business is I mentioned here. I mentioned limits. Yeah, the limits. So the limit is the earliest time in a calculus course when you see the absolute value, and therefore the distance. So this is the distance between the 2 points. So now we have n-dimensional distance, and it turns out that it's just so easy now to define the limit of a sequence in n-dimensional space. So it's so simple that, even though I'm not going to elaborate, it's so simple that it's just worth writing out so that we know where we're going. Okay, so now this time I could write almost exactly the same thing, but I won't. Suppose I have a sequence, so an, and I have a. So these are locations in Rn. Okay, so what I could do now, what is the meaning of a limit? That an is converging towards a. Now this time these are not numbers. These are in fact, let me put letters here that resemble what we have been doing. So we have a bunch of locations in this multidimensional space, and then we want to, in what sense can we use the word limit and that arrow over here? So this is the limit. As n goes to infinity. Oops. I probably should throw out n here because n is reserved for the dimension. So a piece of k, a bunch of points, and then p is its limit. And what is the meaning of it? It is very simple. It is the answer is the distance from pk to p is going towards 0 as k goes to infinity. That's all. So these are pk's, and this is p. The distances get shorter and shorter and shorter. That's all. So that's why distance is so important, because we're replacing the complex geometry of locations in the high-dimensional space. We replace it with distances. And what are distances? They're numbers. Okay, so these are numbers. These are locations, and as I said, it might be complex, multidimensional, hard to visualize, but we replace with this little step, we replace those complex relationships with a bunch of numbers. So in other words, this is a sequence of numbers, and all we're asking it to be is to converge. So the sequence of numbers converges to 0. Okay, so that's all we're saying. And this is a typical example of how we convert convert new problems to old problems. So if you know how to handle limits in dimension 1, then with this little step, we also can handle convergence of sequences and functions too. We can handle them in multidimensional spaces. Okay. All right. So and that's what we're going to do. But it's just so as you can see, it's one line definition, and it is very, very effective. Okay. So and then distances satisfy these properties. As you can see, we justify them primarily by using the reduction to the plane. And finally, we're starting algebra. So here I started to talk about measurements of angles, even in dimension 1. It is actually measured to, there are two possibilities for angles. If your vector is not 0, vector number, it's the same thing in dimension 1. So then what you do is there are still two possibilities, 0 and 180 degrees. And well, that is something we're gonna aim for. So starting with dimension 1, dimension 3, and so on, we're gonna be handling those angles. So this is entirely about angles, and they will appear in all the dimensions. And once again, the point I just made that the situation, look, this situation. Even though I plotted in R2, but every time you have two vectors originating from the same point, it's like two lines, which means that there is a single plane containing those vectors, which means that if you have only two vectors to worry about, I mean, it's the angle, then you can think of the whole thing being planar. So it's all still Euclidean, still two-dimensional. So we'll get back to that. I just wanted to get to this point, to what vectors are to begin with. From what we've just been doing, and that's from points. Okay, so let me proceed this way. So algebra, so we have Rn. You can pick low dimensions if you like. Okay, so PQ points in Rn. Okay, so, and we can ask ourselves, is there any algebra? Of points. And not exactly. Remember, let's not confuse the two things that we have now. We have Euclidean spaces, and we have their Cartesian systems, Cartesian coordinate system on them. The computations of distances or whatever we need in this environment requires algebra, obviously. Look at it on the right. But actually, as you can see over here, it is really not. The distances satisfy certain properties, and none of the algebra is required. As you can see, it's simply it is well. Incidentally, maybe if we stop for a moment, this is a function as well. So g, the distance is a function with the two inputs being the locations in two locations in our space. Okay, so we don't really need those formulas unless we actually have to compute the specific numbers. So everything makes sense even without referring to that algebra. So what I'm talking about is algebra in a more literal sense. Say, for example, what is p plus q? And if we do not have any algebraic Cartesian system associated with this, I have p here, q there, and what is the meaning of p plus q, if any? There is no zero, there are no units, there is no direction. What's the meaning of p plus q?
The distance between each other?
No.
Shouldn't just be the sum of each of the components, component-wise?
Well, look at it. Once again, there is no Cartesian system.
So nothing.
There is no meaning. That's the answer. So no Cartesian system. There is really, adding 2 points, there is no particular meaning to that. What about p minus q?
sign difference?
In one-dimensional, I suppose it will. In one-dimensional case, I think what you're saying is that if we look at the sign of this, we'll know whether on which side they lie from each other, probably. But what I'm suggesting here is there is a meaning of this. It is a displacement. Well, actually, the other way around, but a displacement. So if we're talking about location, we subtract, it will be a displacement. Except that the problem with this algebra is that the difference of P and Q is not, of two locations, is not a location. It's a vector. Okay, so this is a vector. In fact, maybe you'll tell me how I should, what that vector look like. What should I denote it?
It has its tail at
Yeah?
Q and ends at P.
QP. Okay, so who has seen this in high school? Please raise your hand. Points, 2 points, determine a vector, initial point, terminal point. Seen it? A few of you have seen it in high school. So that is very good because it really gives us a foundation to build, to go towards algebra. And it is a little bit slightly different from high school because you probably didn't do subtraction, but you did this, right? So subtraction, seeing algebra, maybe you didn't do or did or didn't do, but at least the understanding vectors as simply pairs of locations. So a vector is a pair of locations. A pair, once again, I'm referring to order pair. So PQ is not the same as QP. Same. P and Q, not the same. Not equal to QP. Okay, and then we could do algebra with it, as I just indicated. Starting with, as we can see, the algebra that I already carried out. So one location minus the other location is the displacement, which is a vector. Okay, so that's what this picture says. You can turn it around. So if I take this and turn it around, then what is it? Q plus. Hold on a second. QP is equal to my location is Q, my displacement is QP, the outcome is
P?
P. That's right. So even though that picture is of numbers, but we're certainly not talking about numbers. So because if this is Q and this is P, this is what we're talking about in QP. Okay, and you could go one way or the you can go many times of this kind many times of displacement. A sequence of displacement is another possibility. But that's what this operation is. So you could, there's a mismatch of the entities involved in this algebra, unlike everything probably you've seen elsewhere. And that is usually you add numbers. You add two numbers, you get a number. Okay, and that is a typical situation. But that's another possibility. A location, a point in space, plus a vector which has the same. That's crucial. Same initial point. Point as Q, so location is Q. The vector that we only allowed to use should have the same initial point. Okay, and then the answer is the terminal point. And the other way was it head and tail. Head and tail. So let's see. So the initial point is the head, and the terminal point is the tail. So that's a little bit of algebra. How we can carry this out now, no problem in any dimensional space. Okay, as you can see, if you look at this picture, what is the dimension? I don't know, it doesn't matter whatsoever, because 2 points, they connect there, they lie on the same straight line, whether, no matter what the ambient dimension is, and all this algebra still makes sense. Okay? Before we move to actual vectors, let me make sure that we know what the connection to the to calculus, and let's think about that. Our displacement. So once again, so this is say P and P. So locations, and this is the displacement. What I'm talking about here is a step towards, well, you tell me a step towards what? What concept in calculus that this is supposed to take us to?
Work?
No. But if you were referring to the possibility of this actually takes us to a parametric curve. You just jump from one point to the next, and then you can, on the parametric curve, you can compute the work. But what I'm talking about is simply something more basic, and that is the displacement. Displacement, the meaning of displacement. Okay, displacement. What is it? It is the change of location, which is what we just said. Well, if I take the change of location and divide it by the change of time, what do we get? What is this?
Difference quotient?
It is a difference quotient, but if difference quotient, yes. What I'm trying to say, this is the velocity. So if we stick with locations and time, then we're probably talking about motion, and so it's better to say it's velocity, but certainly locations are abstract, and so we could speak of, certainly we can speak of difference quotient, this one, and then we are a step away from the derivative. Okay, so that is the derivative that we are aiming for. In other words, even though, think about, suppose our location is our points, right? These are locations, the points where we are. The time is certainly the extra variable that's not present here. And then what we can do is we could try to compute our velocity by taking a displacement dividing by time. And we already also, that would be just difference quotient. And if we want instantaneous velocity, we already have limits too, almost. We're getting towards that too. So the limit of location over time will give us the derivative of what? A parametric curve. Okay. So in any dimension. So you just take change of location, which is a vector, divide by time. This is when you still need to figure out what you do with vectors, algebra with vectors. That's the next topic. But if you figure out how to divide change of location, which is a vector divided by a number, change of time, there you go, you have your velocity. Okay, you have velocity, and from this metaphor, you move on to the derivative, and then the rest of calculus. The integral is also present here somehow. Well, imagine that my delta t is equal to 1. Then my displacements are the same as the velocity. So I am adding one velocity, the other velocity, third velocity, and what am I talking about?
Sounds like a Riemann sum.
It is. Yeah, it is. And I mean, well, once again, this is. You need a Riemann sum and then take the limit in order to get the Riemann integral. But if your function is to begin with step function, then you don't really need it, and then you can just say it is the Riemann integral. So in fact, this is the Riemann integral. So you add, which means the same as integrate. You integrate the derivatives. What do you get? You get the original function, and in other words, I'm referring to the fundamental theorem of calculus. So we'll see that all soon enough when we actually talk about the calculus of parametric curves. But at this time, this is just a way to get started with vectors. And you can see what we need to be able to do with vectors. There are two things already. One is here. We should be able to multiply or divide vectors by numbers. So this is a vector, and this is the number. So once again, we have to multiply vectors by numbers or divide by numbers, and we also should be able to do addition of vectors. Okay, so that comes next. So, well, we'll get to that in a minute. So, okay, so the algebra of vectors now, that's the next algebra of vectors. But we are very careful here, and I'm adding as a caveat, or more like a restriction, vectors that start at the same location. Okay? Vectors that start at the same location. As you can see, it's not necessarily the case. The way we have designed it, a vector can start at any point P or Q, and it goes towards another point P and Q. Okay, so technically, every point in our space has vectors all over the place, sticking to the other directions like this. So that's, say, P. And then there is elsewhere altogether, there's some kind of point Q, and once again, there are vectors of different lengths and in directions. And now the question is, if I pick this vector and that vector, can I add them? No, they have nothing to do with each other. So if in any doubt, I think once again pick those metaphors from physics. So vectors are usually reveal themselves by using physics as a metaphor. It's they're either velocities or they're forces. So we'll get back to these two every time it is necessary. And so you can imagine what we see. So you have a picture here, and as I said, the same picture is present for every location. Okay, so then it's like you can think of it as a flow, and then in each location you could go in any of the directions. But even though velocity can be added, for if you're flowing, if you are swimming through a stream, then it makes sense to add vectors, your actual effort. On one hand, maybe across the stream, and then the stream itself, right? So I'm trying to go straight across the stream, and then and the stream also carries me along to the right. Okay, so then it makes sense to try to like this. So that's my stream, and this is me. Okay, swimming. So we know that the resulting displacement and the resulting velocity will be in some kind of diagonal velocity depending on the proportions of these two velocities. Similarly with forces. Okay, so you have one person pulling this way and the other one pulling this way, and then once again the resulting force will be in some diagonal direction. So all of these work, but they have to be applied at the same location. So this has got to be the same. So if these two have different applications, it's like if I'm taking an object and I apply one force here, one point there, you cannot just go ahead and add those two, because unless they are exactly pointing in the opposite direction, then you're in luck. But otherwise, pulling it this way and that way, it's the effect of the total effect of these forces is not obvious. So just the physics of it. There will be some kind of rotation around the center of mass, whatever is happening. But just if you see in physics of this kind, then you know that you're not supposed to just add forces unless they are directly applied at the same location. So, so the answer is no, then we cannot add vectors unless they start at the same location. But if they do, then any two vectors can be added. Okay, so, and following the same idea as I just said, the idea is that it's going to go in somewhat diagonal direction. So this is the idea. One vector, let's say x, another vector y. They apply to the same, they're starting, the initial point is the same, which means that we can add them, and you might remember this from elsewhere. How do we add vectors?
Add components.
No, well, see, I want to start with component 3. Just like we started with locations, we are thinking, especially in dimension 1 to 3, if I'm applying a force, lifting it, there are no coordinate system for me to refer to. Okay, so the force or velocity exists apart from any Cartesian system that we might impose on this world. In high dimensions, then maybe it's made up anyway. So we're not as much concerned, but everything should make sense regardless of whether there is a Cartesian system that helps us. It only helps us, and that's where it comes from. It helps us to do geometry in an algebraic way. Okay, so we pre-measure everything, and then we can do measurements of measurements of distances. We do computation of distances, and similarly, there will be algebra of vectors that is based on the Cartesian system, but this thing exists apart from it. Okay, so we should be able to understand what that is without referring to the coordinates. So you remember this picture? Anyone?
Tip to tail? With a parallelogram?
Right. Yeah. So one way of proceeding is to let me just do it, rather than do a construction, let me just show what the outcome looks like. We know that it should be roughly the total force or the total velocity. It should be in somewhat diagonal direction, but the answer is a parallelogram. Okay, that's, joke. It is a joke that you may have heard, that there's a parallelograms is exactly what they scare kids with those. But this is where actually this is kind of useful. I'm creating a parallelogram based on those two vectors. And once again, there is no need to think about the dimension of the space. Two vectors, they always are within the same plane, so the whole thing is two-dimensional, even though that two-dimensional thing might be containing in a high-dimensional space. Okay, so I make a parallelogram. Parallelogram meaning polygon with 4 sides, and opposite sides are parallel. That's parallelogram. Okay, so that is indeed what has happened is I took my vector y and I created a copy, for it on the other side. It is against the rules just to shift y elsewhere, because we know that we're not supposed to add vectors unless they are at the same location. So we do not abandon the rule. We just stretch it in such, for the sake of this construction and this construction only. I am so that's the answer. I am making a copy of y with its tail its foot becoming the tail attached to the tail of x. Okay, so as you can see, this is where they were. Both of the tails are this here. But then I take the tail. This is a head of x, but also the tail of y. Well, of a copy of y. Okay, so, and similarly, the same thing happened here. The tail of, the head of y is where the head of y is where the tail of x is attached. Okay, so that's the other point. It doesn't matter. It is really not too complicated to shift stuff around. And the point is then you go diagonally across this parallelogram, and that is the outcome. So the end result is this is x plus y. It is also starts at the same place, same tail as the original ones. So in other words, the good news is that we're not getting outside of our comfort zone where we do addition or algebra of vectors with the same tails. Okay, so we took two vectors with the same tail, we add them together, and once again we have a vector with the same tail. So just like adding numbers, so we're producing that algebraic operation produces an entity, an object of the same nature as the two original ones, just like with numbers and other things. Okay, and the rest of the construction is simply the rest is just how to find it. How to find it, we move stuff around a little bit. Once again, remember that this is like one single plane, like this. So this is a plane. So even though the whole thing might be in a three-dimensional space or high-dimensional space, the whole construction remains within dimension 2. A simpler construction, remember we had two requests, adding vectors and multiplying them then by numbers. Okay, so the second one is even simpler. Multiply a vector by number isn't hard. You literally just stretch it in a particular direction. So let me illustrate this second operation. So this is vector addition. And now we have it's called a scalar multiplication. A scalar is another word for a number. Okay, so we're not trying to multiply vectors. So vectors are not numbers. So even though we are able to add them, and if we're able to add them, by the way, we'll learn how to subtract them too. But we do not multiply them, and certainly we do not divide them. So scalar multiplication means a vector multiplied by a number. So if I have my x here, and so what do I do? It's really a simple idea. If this is x, then this, if I repeat x, once again head to tail, I take my x, this is being the tail, and that's the head. I attach head to tail, and then the end result is, well, this is 2x, as we know. This is x copy, and altogether we already know that this is based on the previous analysis. This is x plus x, right? Two vectors, just because the vector is the same, it still be a vector addition applies. So I add vector to itself, and I end up with this picture, maybe slightly longer, this one. Okay, attach x to its tail, to its head to its tail. Altogether I have 2x, which is supposed to be equal to also 2x, as we know. And indeed, that turns out to be a multiplication. So I multiplied, ultimately what has happened here is I multiplied my vector by 2. And what is the meaning of it? I stretch it by a factor of 2. The only difference is, while it's insufficient, we should be able to multiply by any number. So if I have some real, say, r, then I should be able to annex vector x. So what is the meaning of Rx? And it's a vector of the same direction, but just a different length. Okay. Okay, so these are the two operations that we have. The scalar multiplication is even simpler than the addition because it is in fact one-dimensional. Okay, so addition, unless they're parallel, Yeah, okay, so it's a line. It lies within a line. Okay, so addition within a plane, scalar multiplication within a line, same direction, has to be understood carefully because it is possible that it is reversed. So for example, if this is my x, this is minus x. Okay, so multiplication by a negative number reverses the direction, but it's still, the rest is still the same. Okay, so that's the basic algebra of vectors. Once again, limited to vectors that are starting at the same point. Let me quickly, just for a change, there is an Excel file here. Yeah, so what happens if we represent those points, and therefore we represent vectors as through their coordinates, or technical word is components. So that's what's happening. It's happening here. You can review here the constructions just I had for adding vectors. So this is A and B. A plus B is equal to C. They're starting at the same point, the origin. Okay, then you can see what has happened is that this we started here. I'm attaching head to tail. Okay, then once I attach head to tail, I could go diagonally from the beginning to the end. Okay, and then alternatively, I could see that in fact what the result is the diagonal of a parallelogram. Okay, so it's all here. That's the whole computation. The point of this, that for one, is we need to discuss the. I tried to show this apart from any coordinate representation, because in fact I could do it this way. Take the last picture, and I could just I could delete all the coordinates altogether. Okay, it doesn't want to delete. Let me try again. I want to delete this. Well, still axes are still here. Well, the point, I could delete all the axes, and as you can see, it still makes sense. The operation still makes sense, even though you do not see any coordinates, any axes. The only thing that we do need to make sure that it's the case we have is the same point of origin. Okay, and so next time we'll talk about what happens to the coordinates and why we need.